What we want to do now is give you an example of how to calculate the net work done on a gas in a cyclic process. So here we have an example where our gas starts out at a pressure of 100 kilopascals and the initial temperature is 300 Kelvin, and the adiabatic constant for this gas is 1.4, and the gas, we're going to move it through 3 different cycles. Right? We're going to compress it adiabatically from 4 liters to 1 liter. Then we're going to cool it at a constant volume back to its original temperature of 300 Kelvin. And then we're going to let it isothermally expand back to its original volume. And we want to know what the net work done with this entire process is. So the way to do this is to construct a PV diagram, all right? And so here we have our initial PV diagram, and our volume is in liters, and our pressure is in kilopascals. And I have my first point here because we know that it starts at 4 liters and 100 kilopascals. And then what we want to do is find the final pressure after this first compression, okay? And again, the adiabatic compression is going to cause no heat transfer to or from the system, so this compression is going to raise the internal energy of the gas simply from the compression itself, and thus the temperature as well. So what we first want to do is find P final, because we know V final is going to be 1 liter, but we want to find where on my pressure axis this is. This can be done through the adiabatic equation. Remember, the adiabatic equation looks like this. P times V to the gamma equals my constant. And what we can do is set our initial values of P and V to this constant must be equal to my new P and V values up here, but I know what my V is and I know what gamma is, so then I can substitute those in and solve for my final pressure. And so we know that this is 100 kilopascals and this is 4 liters. And I'm going to leave my units in kilopascals and liters. So here we have 100 times 4 to the 1.4, and that must equal whatever my final pressure is, times 1 to the 1.4. Well, 1 to the 1.4 is, of course, just 1. So this essentially disappears. And if I multiply this out, I find that this is just under 700 kilopascals. For all intents and purposes, we can say that it's 700. So the compression is going to move the gas from 4 liters to 1 liter, and it's going to compress it from, or the pressure is going to increase from 100 kilopascals to 700 kilopascals. And if you think about it, that makes sense. If I'm pressing down on the gas, then that is going to decrease the volume and raise the pressure. And remember, this is adiabatic, so it's going to follow a path something like this. And then we cool the gas back down to its original temperature. And then we isothermally expand it to its original pressure, original state actually, the original volume. Right? So we have this kind of cycle, and we want to know what the net work done with this cycle is. And the net work is going to be the area inside this curve, right? It's the area inside the curve. So we want to find the area underneath the adiabat, right? the area under the adiabat. That's what that line is called. An adiabatic line connecting 2 points is an adiabat. And then we want to subtract off the area under the isotherm. And the net is going to be what's left here in the middle, right? And the net is what we're after, all right? So our strategy is find the work done under the adiabat, find the work done under the isotherm, subtract them off, and the net result is going to be the net work done on the gas. So our first step we want to find the net work done for our adiabatic process. And remember, that work is equal to negative P dV, the integral of P dV. And this is from V1 to V2. And we're going to use our adiabatic equation because P is going to equal C over V to the gamma. Or we can write this as C times V to the negative gamma dV. So this is the function we're now going to integrate, and we're going to integrate it between our two volumes. Well, if we go ahead and integrate this, the integral of V to the negative gamma is V to the negative gamma plus 1 divided by negative gamma plus 1, evaluated between V1 and V2, right? And here I have a negative sign, and I essentially have a negative value here because gamma is 1.4, so this is negative 0.4. So if I get rid of this negative sign, it's the same thing as flipping the sign here, so this will be gamma minus 1. And now what I can do, I have to evaluate this V between V1 and V2. So I'm going to be taking a difference, right? But remember that C equals PV. So I can rewrite this, C equals PV to the gamma, and so I can rewrite this as PV to the gamma times V to the negative gamma plus 1 evaluated between my two endpoints. And V to the gamma times V to the gamma minus 1, or negative gamma plus 1, is going to give me just V. So this is P1, or I'm sorry, P2 times V2 minus P1 V1 over gamma to the negative 1. Right? That is just my work. And so P2 we said is 700 times 1 liter. So this is 700. And here we have 100 times 4, so my net is 300 on the numerator divided by 0.4. And the result is a little over 700, all right? We'll go with 700 for now, but it's a little bit over 700. All right, so that's how you can find the work underneath this adiabat, all right? And that represents the red, if you can see it, but it's the entire area under the red line here, okay? Now, the second part of our cycle was done under constant volume. So when we look at the integral of P dV, there is no dV because there is no change in the volume, so that particular process does not contribute any work to the cycle. Now we want to find the area under the isotherm. And if you recall, the work under an isotherm is negative nRT times the logarithm, of V2 over V1. And the isotherm is at 300 Kelvin because that's where we cooled it to during this process here. This would be, say, A, B, and C. So moving the gas from A to B was the adiabatic compression. B to C is the isovolumic expansion, and then C to A is isothermal expansion. All right, and so the work done here is this, and nRT is just equal to PA because, PV, because PV equals nRT. So I can write this as negative PAVA times ln of, in this case, this would be the volume at C divided by, the volume at A divided by the volume at C. So the volume at A divided by the volume at C, and PA is 100 and VA is 4 liters, so this is negative 400 times the logarithm of 1 over, 4 over 1. And this is approximately negative 550. So the net work done on the gas is going to be equal to 700 plus the negative 550. And this is, of course, all in joules. So approximately 150 joules of work was done on the gas, net, over the course of this entire cycle. Now, what happens is, because the gas is returned to its original state, that net work has to go somewhere. That work is going to go into heating the environment, all right? So I hope that example was helpful. I know we kind of flew through some things, but hopefully you'll be able to digest what we did, and we will see you next time.